Good evening viewers. Once again we are back to this course on convex optimization. Yesterday if you had remembered, we had just spoken about these facts that we have proved what is called the Rockefeller-Shenichny condition, which is a necessary and sufficient optimality condition for a convex function f to be minimized over a convex set C. Of course, we have proved that it is necessary, and the sufficiency is left as a homework to you, which you can do. Today we are going to go back a bit more and use this power of the convex calculus, that is how we will see how we can exploit the max function. We had spoken yesterday about the max function. If I can just go back, here we have spoken about the subdifferential of a max function, where each of the individual f's which make up the max function, that is max of f I x, that is this f1 x, f2 x, fm x, each are convex and differentiable, and this function f is also convex, which is already well known, which we have spoken earlier. Then the subdifferential, just a moment, is this. So, today we are going to see that okay, if I have to minimize a convex function f x over x element of C, but this time my C is defined by inequality constraints. And each of these constraints are themselves convex. So, I assume that this is f is convex and differentiable, and g I x are also convex and differentiable. Let me assume that this has a minimum, let x bar. So, this is my convex programming problem C p, and let x bar solve C p. So, x bar is feasible, that it satisfies all g I x bar is less than 0, and for every x which satisfies these constraints, f of x is bigger than f x bar. That is the meaning of f x bar solves C p in the global sense. Of course, for a convex problem there is no local minimum. Of course, you can convince yourself that this set C, which is a feasible set of the programming problem C p, is a convex set once I know that all the functions g i's are convex. In fact, it is also a closed set, because each of the g i's are defined from R n to R, and any function defined from R n to R is any convex function defined from R n to R is a continuous function. Now, so what information I have about this is convex and closed. Now, once I know these facts, then I look into the following problem. So, if x bar is solving this problem C p, then x bar also solves mean f x subject to x element of R n, where f capital F of x is the convex function given by max of f x minus f x bar g 1 x g m x. You can try out again as a homework to prove this fact, that whenever x bar solves this problem, x bar will solve this problem. Now, of course, all of these are convex functions. So, capital F is a convex function. So, as homework you figure out, is f continuous and why. Now, once I know this, I can immediately write down the optimality condition that 0 belongs to del of f of x bar. Now, f is a max function, then I can calculate the optimality conditions by applying the calculus rule for max functions. Now, once I know this, what shall happen? How do I now calculate the j x bar set corresponding to f? So, corresponding to my function f, how do I calculate the index set j x bar? In order to do so, I look into this fact that okay, consider all index I. Okay, let us consider all index, consider I which belongs to any one of these indexes such that g I x bar is equal to 0. So, if you take some I which for which this is satisfied, these constants are called constants which are active at x bar. So, this would imply one important phenomena, important thing, that I will collect corresponding to x bar all the indexes I belonging to this index set, that is this is one among the constant indexes, such that g I x bar. Now, if you look at this function, if I put f x equal to f x bar, this becomes 0, and for all the active indexes, that is for all I belonging to the I x bar, I would immediately have g I x bars are also equal to 0. So, when x is equal to x bar and for all other x's g I x is strictly less than 0. So, f of x bar is actually 0. So, this is something you have to be very carefully noting down, that f of x bar is actually 0, and this 0 is achieved at this point, right, which I can write as g 0 if you want, g 0 x. So, this consists of j x consists of the index 0 as well as the active index set corresponding to x bar. So, j x bar consists of the index 0 union I x bar, which is this. Once I know j x bar and I knowing that all these are differentiable, I know that 0 element of del f x bar, which is equal to the convex hull of grad of f x bar this particular set union grad of g I x bar such that I is belonging to I x bar. So, which means you have to, so 0 must be an element of the convex hull of these elements of these sets. So, there would exist some lambda naught, lambda 1, lambda 2 dot dot lambda m, all non-negative, that is all greater than or equal to 0, such that you have 0 equals to lambda naught grad of f x bar plus summation I belonging to I x bar lambda I, not I here I should not put lambda 1, lambda 2, lambda m, here I should put lambda I with I belonging to I x bar, that makes correct sense, lambda I grad g I x bar. Now, let us set lambda I is equal to 0 if I is not in I x bar, that is whenever g I x bar is equal to 0, lambda I would be equal to 0. So, now I can bring in this fact in a much simpler way. So, I can now put in lambda i's to be 0, I can just put 0 0 0 for all the i's which are not in I x bar, but then I have to account for this behavior of lambda I. So, there must be some additional condition that lambda i's are such that lambda I into g I x bar would be equal to 0. So, these would lead to the following condition, that lambda naught grad f x bar plus lambda 1 grad. So, we have two conditions now, grad g 1 x bar. So, I cannot just arbitrarily say that all the lambdas corresponding to lambda I is corresponding to g I x was strictly less than 0 is 0. Once I have assumed that to give this full expression, then automatically a condition arises, and that condition is at lambda I times g I x bar is equal to 0, that is both of them cannot have strict inequality at the same time, that is this cannot be strictly greater than 0, this cannot be strictly less than 0. This fact has to be always maintained by the Lagrangian multipliers or the Kuhn-Tucker multipliers, as we will soon call them. But if you observe here, there is also one important thing which we have not stated. Now, these lambda naught lambda i's are elements forming a convex hull. So, an important thing that one should have stated here was that lambda naught plus summation I element of I x bar lambda I is equal to 1. So, basically 0 belongs to the convex hull of some set which comes from the max function. Now, what does this mean? Each of them are greater than or equal to 0, their sum is equal to 1. So, all of them cannot be 0 at the same time. So, and of course, for I naught element of I x bar we have taken everything to be 0. So, what I would also have the third condition is that the vector lambda naught lambda 1 lambda m is not a 0 vector. This is a very, very important condition, and the condition that you get here is called the Fritz-John condition or the John condition. Fritz-John conditions or just the John conditions. So, Fritz-John presented his condition way back in 1948 and he submitted it to the Duke Journal of Mathematics, which was rejected and then published in a conference proceeding. Later on, Karush-Kuhn-Tucker condition or the Kuhn-Tucker condition came from here in 1951. Now, let me assume something additional which I have not assumed earlier. Let me assume this fact that this set C, the feasible set, has an interior. So, this is my additional restriction. Why I want to put this additional restriction? Note that I have said lambda naught lambda 1 lambda m, the whole vector is not equal to 0, but I did not say that lambda naught need not be 0, lambda naught could be 0, and if lambda naught is 0, then we are in a very, very bad situation, that we have a problem where lambda naught is 0 and grad f, which is gradient of the objective function, it plays no role in the computation, as a result of which things might not turn out as you want it to. So, the representation of f goes immediately from the optimality condition, which is not a fair thing. So, Kuhn and Tucker in 1951 imposed certain conditions which are not now called the Kuhn-Tucker constant qualification, which we are not going to harp here, but an important assumption was given in 1952 by Slater condition, which says C has an interior, the feasible set, which means there would exist an x hat. So, he has, why this condition is imposed? That condition is imposed to stop lambda naught from becoming 0. So, in the John conditions, which is this set of 3 conditions, lambda naught could become 0, stopping the representation of f from the expression in f from the optimality conditions. In order to stop that, that is, in order not to make the optimality conditions look abnormal, you have this additional restriction to stop lambda naught from becoming 0. So, integrity means there exists an x hat in Rn such that Gi of x hat now, once I know this, let me make an assumption like this and I will then show that lambda naught cannot be 0. Now, let lambda naught be equal to 0 even if Slater condition holds. Now, once you do this, once you put lambda naught is 0, you will have lambda 1 grad g1 x bar plus lambda m grad gm x bar is equal to 0. Now, observe that lambda 1, lambda 2, lambda m cannot be all 0 because lambda naught is 0. So, one of the among the this vector is non-zero. So, if lambda naught is 0, so the non-zero vector non-zero component must lie among lambda 1 to lambda m. Now, we know that whenever I is not in I x bar, lambda i's are anyway 0. So, I can write this as lambda I times the gradient of G I x bar. So, I element of I x bar. You see, because lambda since lambda I is equal to 0 for I not in I x bar, it would imply that this is equal to 0. Now, the non-zero components must lie among these I belonging to I x bar, because when I is not in I x bar anyway lambda is 0. So, you have lambda naught 0 and all these are lambda is 0. So, remaining part the non-zero component must appear. So, there is a non-zero component here. Okay. Now, how can I use the Slater condition? Let us see. Now, for any I element of I x bar, G I x bar is strictly less than 0. Now, look at the convexity equation when functions are differentiable and look at this for this particular pair x hat and x bar. X hat is the point where the Slater condition is actually getting satisfied, and so this is bigger than gradient of G I x bar x hat minus x bar. Okay. Now, G I x bar is sorry, I made a mistake. When G I is in I x bar, G I x bar is equal to 0. Sorry. So, G I x bar is 0, G I x hat is, so what remains here in this expression? Now, G I x hat is strictly less than 0. So, what I get from the above is gradient of G I x bar x hat minus x bar is strictly less than 0 for all I element of I x bar. Now, among these elements there is one lambda I which is non-zero, at least one. So, if I multiply by that lambda I with the corresponding grad G I x hat minus x bar, that would also remain to be a strictly negative quantity. So, that would imply in general when I multiply by the lambda I for each corresponding I and sum up, what I will get is summation lambda I gradient of G I x bar I element of I x bar x hat minus x bar is strictly less than 0. This is in contradiction with the fact that here I have this is equal to 0. So, if I take inner product with any vector, if I take the inner product of any vector with the 0 vector, that will give me 0. So, but if I put this condition as the condition A, but from condition A we have so here is a contradiction. Here is a contradiction. Now, once you have this contradiction, so you declare that okay, your initial hypothesis that lambda naught lambda 0 is wrong, and so we conclude that lambda naught is strictly greater than 0. So, now I have this equation lambda naught grad f x bar plus lambda 1, this is called the Lagrange equation or the KKT equation, very now I know that lambda naught is strictly greater than 0. So, I can divide both sides by lambda naught. So, I will call lambda I by lambda naught as lambda I bar. So, what I have proved that if Slater's CQ holds, and this is of course greater than equal to 0 because each of them is greater than equal to 0, this is greater than 0. If Slater condition holds, there exists lambda I bar greater than equal to 0 I from 1 to m such that number 1 grad of f of x bar plus lambda 1 bar grad g 1 x bar lambda m bar grad g m x bar is equal to 0, and number 2 is lambda I bar g I x bar is equal to 0 for all I. Now, this third condition in the Fridtjohn one, this is no longer required because lambda naught I have proved to be strictly greater than 0. So, lambda naught is basically 1. So, Fridtjohn KKT condition is Fridtjohn condition with lambda naught equal to 1. So, this holds if you have some additional condition. So, what we have got here is the famous Karush-Kuntaker condition. It now goes by the name of Karush-Kuntaker condition. So, I think one of the first papers who possibly gave this name Karush-Kuntaker condition was a paper which was called the modern multiplier rules, which appeared in 1980 or 81 in the American mathematical monthly. It is called modern multiplier rules. By P.H. Porciau, American Math Monthly. It was a beautifully written article, and it says that though Kuhn and Tucker had independently derived this condition, so this was known to Karush way back in the end of the 30s, early 40s, I guess. So, now it is called the Karush-Kuntaker conditions or the KKT condition. It became famous in the 1951 seminal 1951 paper by Kuhn and Tucker, Harold W. Kuhn and Albert W. Tucker, both from Princeton. It is very important to remember that even if Karush had these ideas slightly ahead, that does not diminish the value or the worth of the Karush-Kuntaker or the KKT condition or this paper by Kuhn and Tucker, because Kuhn and Tucker in that paper demonstrates with an example why example where lambda naught becomes 0, and they did it even for just differentiable functions. They found the necessary condition, not as we have done for convex functions, and they did not talk about Slater condition, which came slightly later. They spoke about a general geometrical optimality condition, geometrical constant qualification or condition on the constraints, which is called the Kuhn-Tucker constant qualification. And furthermore, this famous paper had also given results for multi-objective optimization, and that is also very important. So, this paper has a huge worth in the optimization community. As Professor Harold Kuhn once told me that once he was inside a conference he was told to introduce Professor Tucker, and he said, I am Kuhn and he is Tucker, and that is all, everybody knows what it is. So, now what we have got here is a necessary condition, that you have given me a solution x bar and I showed the condition that x bar should satisfy provided the Slater condition holds. We will arrive at this condition through various routes. So, there are many different paths to the Karush-Kuntaker condition, and you can immediately understand that 2011 was the 60 years of KKT condition. Now, when the functions are convex, the question is this also necessary, that is, if there is an x bar and if there is some lambda bar which satisfies all this, is my I know whether that x bar is actually a global minimum. The answer turns out to be yes, and let us see how to do it. Look at the definition of a convex function when they are differentiable. Now, you have f x minus f x bar, and this is, of course, you know, take any x in the feasible set in C. Now, take for any I, for all I, g I x minus, say take the same x, g I x bar is again for each I. Now, you can multiply by lambda I, because lambda I is greater than equal to 0. So, there is no harm in multiplying this set by lambda I, and then once you multiply by lambda, you add these inequalities. What you will get is so I am multiplying by lambda I bar, sorry, summation lambda I bar grad g I x bar I element sorry, I is equal to 1 to m, I equal to 1 to m x minus x bar. Now, let us just apply these conditions. So, you know, from this condition it is immediate that this right hand side is 0, because this is 0. So, what I have is f x minus f x bar plus summation lambda I bar g I x. So, minus summation lambda I bar g I x bar this is greater than equal to 0, and if you observe this second condition, which is called the complementary slackness condition, this is called the complementary slackness. which says that both of them cannot be slack at the same time, that is lambda I cannot be strictly greater than 0 and g I x also cannot be strictly less than 0 at the same time. Both of them can be 0 at the same time, but both of them cannot be having strict inequalities at the same time. So, now this is 0 from this condition, condition 2, this part is 0, is 0. So, what I will have is f x minus f x bar, taking this thing to the other side. Now, as x is in C, that it is feasible, g I x is less than equal to 0 for all I. This would imply, because lambda is bigger than 0, I is equal to 1 to m lambda I bar g I x is less than equal to 0, but I have put a minus sign. So, what I would finally get is that this is greater than equal to 0. So, this would imply for all x in C, because x was an arbitrary element in C, f x minus f x bar is greater than equal to 0, showing that x bar is indeed the minimum.